Hello dear students. So we have studied the group of integers modulo n, which was 0, 1, 2 up to n minus 1. Okay, but we have seen that with respect to multiplication this doesn't form a group in general. Okay, but we have something else in case of multiplication modulo n, and we will do it now. Before doing that, I need some idea about relatively prime, the concept of relatively prime integers. Okay. Relatively prime. So in your school days you had learned something about GCD, or that is called greatest common divisor. Greatest common divisor. Okay. Or in other words, this is also called HCF, highest common factor. Okay, highest common factor. So suppose the HCF of or GCD of 12 with 14. Okay, that is 2. 2 is the highest common factor between these two. 12 can be written as 2 into 6 and 14 can be written as 2 into 7. Okay, so there is no other common factor which is larger than 2. So here GCD of 12 and 14 is 2. Okay, but see, GCD of 12 with say something like 25, this is actually equal to 1, because 12 is the only way that we can write is 12 into 1, and 25 is 25 into 1. Okay, but there are no other common factors except 1. Okay, so GCD of these two numbers is 1. So when this happens, that the greatest number of greatest common divisor of two integers is 1, then we say that the numbers are relatively prime. Okay, so two integers say a and b are said to be relatively prime if GCD of AB is equal to 1. Okay, if their greatest common divisor is 1, there is nothing more common between them. For example, 12, 25 are relatively prime. Okay, so they are not prime themselves. Okay, but in comparison they do not have any common factors, so these are relatively prime. Say something like 3, say 64. Okay, 3 is 64. These are also relatively prime. Their greatest common divisor is 1. Okay, these are relatively prime, right? Okay, so this is what we can do, right? So we need the concept of relatively prime in understanding this group. Okay, say the group of units modulo n. Okay, so this is denoted by un. Okay, so let n belongs to natural number. Okay, actually we take n greater than 1. Okay, sorry, let n belongs to natural number and n is greater than 1. Okay, we have to take n greater than 1. Then the set un of integers less than n, strictly less than n, right, less than n, and relatively prime to n, is a group with respect to multiplication modulo n. Okay, if we take this multiplication modulo n as the operation, then this set of un of integers less than n and relatively prime to n is a group with respect to multiplication. Okay, so this is called, it is called the group of units modulo n. Okay, so say for example, what is this? Say I write something like u10, okay, or u8, right? What is this? u8 is the set of all integers which are less than 8 and relatively prime to 8. Okay, so 1 is relatively prime to 8 because the common factor between 1 and 8 is 1 only. 2 is not relatively prime to 8. Okay, the GCD of 2 and 8 is 2. Okay, so it's not relatively prime. 3, GCD of 3 and 8 is 1, so it's relatively prime. So 3 is a member in this set, right? And say 4 is not relatively prime to 8 because GCD of this 2 is 4, so it's not relatively prime. 5, GCD of 5 and 8 is 1, so it's relatively prime. So 1, 3, 5, 6 is not there because GCD of 6 and 8 is 2, so it's not relatively prime. But 7 is there, GCD of 7 and 8 is 1. So okay, 1, 3, 5, 7, this is a group with respect to multiplication modulo 8. Okay, multiplication modulo 8 operation. That means A multiplied with B modulo 8 means the remainder when A into B is divided by 8. Okay. Another example, U10. Okay, what is U10? U10 is the set of all integers which is less than 10 and relatively prime to 10. So 1 is relatively prime, 3 is relatively prime, 5 is not relatively prime, 6 is not there, 7 is relatively prime, 8 is not relatively prime, 9 is relatively prime. So 1, 3, 7, 9. This is a group with respect to multiplication modulo 10. Okay, so with respect to this, it's a group. What about U5? See, what are the elements in U5? 1, 2, 3, 4. Okay, see. So observe something interesting. What is U3? U3 is 1, 2. Okay. If I write something like U2 is just singleton 1. Okay. So there is nothing called U1. U1 is an empty set. Okay, there is no integer which is strictly less than n1. No positive integer. Okay, how did I define this set of? I have to write positive integers. Okay, positive. Please correct this. It should be the set of positive integers less than n and relatively prime to n. Okay. If you do not write positive, then there may be other elements in this set also. Okay, so that is important. So U1 cannot be there. U1 is an empty set. Okay, so that is why we consider n greater than 1. Okay. What will be U7 if you see nicely? U7 is 1, 2, 3, 4, 5, 6. See. So what is the difference you see? In U10 you have just some numbers and there in between the numbers are skipped. But in U5 you have all the numbers from 1 to 4. In U3 you have all the numbers from 1 to 2. Okay, in U7 you have all the numbers from 1 to 6. Let us see a few more examples. Say something like U8 already we have seen. U9, what is U9? So 1 is already always there. So 1 is there in each UN, right? So 1, 2 is there, 4 is there, 5 is there, 7 is there. Okay, 8 is also there. So 1, 2, 4, 5, 7, 8. Okay, so the numbers are not in serial, means consecutive, not consecutive. U11 on the other hand, you see U11 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what is interesting is you get all the numbers from 1 to up to n minus 1. Okay, so if you observe nicely, these numbers are actually prime numbers. 5, 3, 2, 7, 11, they are prime numbers. Okay, so a prime number has exactly two divisors, positive divisors, that is 1 in itself. So it is not divisible by any other number, right? So that is why every other number from 1 to n minus 1 will be always relatively prime to a prime number. Okay, so if n is prime, then un is nothing but, okay, then un is actually 1, 2, 3 up to n minus 1. Okay, this one, right? It contains all the integers from 1 to up to n minus 1. Okay, so we are getting something similar to Zn. So it's actually Zn difference singleton 0. Okay, right? So that type of set. Zn is all the integers from 0, 1 to up to n minus 1. Okay, all the remainders. Here we are not having remainders. Okay, so these are actually called units modulo 9, modulo n. Okay. means with respect to modulo n operation, these elements, these numbers will have multiplicative inverse. Okay, that is the thing. So if n is prime, then un is exactly equal to the set of all numbers from 1 to up to n minus 1. Okay. So we will not prove the case in general that un is a group. Okay, it will require some number theory, so which I don't think it's necessary for the past course. So we'll do some results, particular results. Okay, show that. So we will consider for some fixed values of n and just construct the composition tables and all. Okay, so that show that u10 or say u8 is a group. Okay, is a group with respect to multiplication modulo 8. Okay, so how will you do it? We'll construct the composition table. Okay, so from the composition table I'll get all the idea about closed property, I'll get idea about commutative property, I'll get the idea about this existence of identity, I'll get idea about existence of inverse. Only thing that will left is the associative property, and that will just state, as already we have explained in the earlier class, we'll just state that multiplication modulo n is an associative proposition. Okay, so everything else we'll get it from the table itself. So we construct the composition table. Okay. Composition table. Okay. Or it is also called Kelly's table. Okay. This composition table, this is also called Kelly's. Kelly was a mathematician. This is also known as Kelly's table. Okay. Kelly's table for u8, which is equal to u8 is 1, 3, 5 and 7. Okay, this is u8. Okay, so let us try to construct this. u8 is this. Okay, so this is the thing. 1, 3, 5, 7. Okay, and this was also 1, 3, 5, 7. Okay, so here we have multiplication modulo 8. And then here I have 1, 3, 5 and 7. Okay, here also 1, 3, 5 and 7. So 1 into 1 is 1, 1 into 3 is 3, but remember we have to take modulo 8. Means after multiplying we have to divide the number by 8 and take the remainder. 1 into 5 is 5, 5 when divided by 8 is 5. 1 into 7 is 7, when divided by 8 it's 7 only. Okay, means the remainder. 3 into 1 is 3, remainder is also 3. 3 into 3 is 9, but the remainder here will be 1. Okay, 3 into 5 is 15, but the remainder will be what? If we divide 15 by 8, the remainder will be 7. And 3 into 7 is 21. 21 if you divide it by 8, then the remainder will be 5. Okay, then 5 into 1 is 5, remainder is also 5. 5 3 is a 15. 15 when divided by 8, the remainder is what? 7. Okay, and 5 5 is a 25, when you divide by 8, remainder is 1. 5 7 is 35, when you divide by 8, the remainder is 8 4 is a 32, the remainder is 3. Okay, 7 this is 7. 7 3 is a 21, if you divide by 5 8, it's 5. 7 5 is a 35, 35 it's 3, and 7 7 is a 49. 49 if you divide by 8, the remainder is 1. Okay, so from the table you see each this product that we get is an element inside u8 only. Okay, so from the above table we get, so let us list it one by one. Say A into B, this product is in un or u8 for all A, B inside u8. Okay, this is the closure property. Okay, closure property is satisfied, right? Number 2, we also get A into B8 is equal to B into A8 for all A, B inside u8. Okay, so we get commutative property also. So even though it's not necessary for a group to be commutative, okay, but here we get a commutative group actually. And also if we talk about identity element, here the identity element is 1 is the identity element. Okay, 1 multiplied with any other element is the element itself. Okay, so number 3, 1 belongs to U8 is the identity. Okay, is the identity, right? And then number 4, we have to talk about inverse. Okay, what are the inverse of this each of the elements? Okay, so the inverses of 1, 3, 5, 7 are what? So you have to look for this, the entries where we get 1. Okay, so there immediately you will get the inverses. So inverse of 3 is 3, inverse of 5 is 5. Okay, inverse of 7 is 7 here. Okay, so inverses of 1, 3, 5, 7 are 1, 3, 5, 7 respectively. Also, the associative property, also we know multiplication modulo 8 is an associative operation. Okay, is an associative operation, right? So from above we conclude that this U8 is a group with respect to multiplication modulo 8. Okay, so this is the proof. So it's quite simple, you can do it easily, right? So let us try another one. We'll prove something like this. Show that U10, which is equal to 1, 3, 5, 7 and 9. Okay, 1, 3, 7, 9 is a group with respect to multiplication modulo 10. Okay, so how will you do it? So we will just construct the table. We construct the Kelly's table. Construct the Kelly's table. Okay, so we construct this table. Let us try to construct. This is 1, this is 3, 7, 9. Okay, this is here also. So it's multiplication modulo 10. Here you have 1, 3, 7 and 9. Okay, 1, 3, 7 and 9. So 1 into 1 is 1, 1 into 3 is 3, 1 into 7 is 7, 1 into 9 is 9. 3 into 1 is 3, 3 into 3 is 3 is a 9. If you divide by 10, remainder is 9 only. 3 into 7 is 21. If you divide by this 3 into 7 is 21. If you divide by 10, the remainder is 1. 3 into 9 is 27. If you divide by 10, the remainder is 7. Okay, 7 into 1 is 7. 7 into 3 is 21. If you divide by 10, it's 1. 7 into 7 is 49. If you divide by 10, the remainder is 9. 7 9 is 63. 63 if you divide by 10, the remainder is 3. Then sorry, this is not 8, this is 9. So 9 into 1 is 9. 9 into 3 is 27. If you divide by 10, it's 7. 9 7 is 63. It's 3. 9 is 81. 1. Okay. So from the table you see it follows that this each entry is an element in U10 only. Okay. So exactly we can write whatever we have written here. Okay. In the earlier case, the first two parts are same. The next parts are little bit different. Okay, so from the table we see that number one, this closure property A into B mod 10 is in U10 for all A, B inside U10. Okay. And number 2, we also see that A into 10 B, this is equal to so in the earlier case also please write not only a group, is an abelian group. Okay. So if in your question it is asked that show that it's an abelian group, then you can write about the commutative property, otherwise it's not required. Okay, it's optional. If it is given that it's an abelian group, show that it's an abelian group, in that case you need this, otherwise you don't need it. Okay, to show that it's a group, we do not need this. Okay, so this is optional. If you want, you can write. And of course it depends on the question. If in your question it is given it's an abelian group, okay, then you have to do it. Okay, number 3 is we see one belongs to this. Number 3, let us write associative property. Okay, or no, here we have written from the table. Okay, so from the table associativity is not clear, we have to write it separately. Number 3 is one belongs to U10 is the identity. Okay, is the identity element, right? And number 4, the inverses of 1, 3, 7, 9 are respectively. So inverse of 1 is 1 only. Inverse of 3, if you see the table nicely, inverse of 3 is 7, and inverse of 7 is 3. Okay, and inverse of 9 is 9 itself. Okay, so 1 inverse of 3 is 7, inverse of 7 is 3, and 9. Okay, and also the associative property. Okay, so please mention about this associativity, just like I have mentioned for the earlier one. Okay, just like earlier one. So it's a group. Okay, U10 is a group with respect to multiplication modulo 10. Okay, similarly you can try other exercises. Show that U5, which is equal to 1, 2, 3, 4, this is a group with respect to multiplication modulo 5. Okay, so like that. So these things can be done. So almost we have done all the examples of groups. Yeah. Okay. Determinants also we have done, special linear group, general linear group. So everything we have done. So we have almost covered the first unit. First unit is covered. The second unit here. The second unit is this cyclic groups, subgroups, related theorems, and problems. And then you have cosets, their properties, index of a subgroup. Okay. So we need to start something about subgroups and all. Okay. Then so let us start with subgroup. Or before that, cyclic groups. Cyclic groups are also there. Yeah. No, before cyclic group, I think we should do the subgroup thing first. Right. Okay, so let us try this subgroups. And before that, let me just give you some definition for finite groups. Okay. Yeah. Order of a group. Yeah. The number of elements of a group, of a finite group, let's say finite group, this group having finite number of elements. Okay. The number of elements of a finite group is called the order. Okay. It's called the order of the group. Order of the group. Okay. So for example, order of say Z3 with respect to addition modulo 3, okay, is what? 3 only, because Z3 contains, what is Z3? Z3, the elements are 0, 1 and 2, so only 3 elements are there. So this is called the order of the group Z3. Okay. Similarly, another say order of say U10 with respect to multiplication modulo 10. Okay, this group is what? Is 4. Okay, as we have seen, as U10 is what? U10 is the set 1, 3, 7 and 9. Okay, so order of this is this, right? So several things are there. So in general, order of Zn with respect to addition modulo n, okay, is n. Okay, because the elements of Zn are 0, 1, 2 up to n minus 1. Okay, these are the elements in Zn, right? Next is what is, say, order of un with respect to addition multiplication modulo n, where n is prime. Okay, if n is prime, I know how many elements are there in un. Okay, when n is prime is n minus 1. Okay, because as un, in that case, if n is prime, then un is actually 1, 2 up to n minus 1. Okay, every number from 1 to up to n minus 1 is relatively prime to n, if n is a prime number. Okay, so these are the things, right? Okay, then there are some notations which we will adopt. Okay, so some notations. Okay, some notations. Okay, right. If we have say, let G star be a group, right? Then for any A inside G, this A star A is denoted by A square. Okay, we denote it in this way, A square, right? A star means A square means A operated on A itself. Okay, so similarly we can have something like inverses, right? G to the power 0. Okay, so in particular, similarly A star A. Okay, this is denoted by A cube. Okay, and for the multiplicative operation, so this is called the multiplicative notation. This notation is called the multiplicative notation. Right. If the group is additive, we'll write it something like this: A plus A. Okay, for additive notation, we use the symbol plus. Okay, additive notation, where the operation is almost something similar to addition, just like normal addition or modulo addition. Okay, in that case, we denote this as A plus A is denoted by, instead of A cube, we denoted by n 3A. Okay, so 3A, NA, right? In general, by NA. So in general, A star A, okay, like that, dot star, dot star, n times. Okay, n times is denoted by A to the power n. Okay, and because of associative property, it satisfies the indices, laws of indices. Okay, A to the power n m plus n equal to, like that. So similarly, for the additive notation, is A plus the dot up to A n times. This is denoted by NA. Okay, this is denoted by NA, right? So with this notation, and because of the associative property, and because of associative property, the laws of exponent hold. Okay, so something like this. If a to the power n it's composed with b to a to the power m, this is same as a to the power n plus m. Okay, like that. Similarly, a to the power m, a to the power n whole to the power m. Okay, means this whole to the power m. This actually means a to the power n star with a to the power n star dot 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 dot, dot star a to the power n actually m times. Okay, so this is what is the meaning. So a to the power m whole to the power m. So this is actually equal to a to the power mn. Okay, so this law also holds, right? And then we have something for some notation for identity. Identity is denoted by a to the power 0. Okay, identity is denoted by a to the power 0. Right, where a is any element. Okay, so a to the power 0 always represents identity. Okay, also inverse of say a square or a to the power n is denoted by obviously a to the power minus n. Okay, because in that case we will have in a to the power n star a to the power minus, and this will give us a to the power 0 by the laws of exponent, so which is equal to identity. Okay, so it's a convenience of notation. For convenience of notation, we denote it this way. Okay, so the inverse of a to the power n is a to the power minus n. Okay, so that way it is denoted, right? So we will use this notation. Okay, however, in general for a group a star b or ab, sometimes we do just avoid the composite this symbol also. Okay, the operation, and just write ab. So ab means actually a star b. A to the power ab whole to the power n is in general it is not same as a to the power n into b to the power n. Okay, but for commutative groups it is same. Okay, so in general for a group this ab whole to the power n cannot be written as a to the power n into b to the power n, as the group might not be commutative. Okay, the group may not be commutative. Okay, so in general this doesn't hold commutative. Okay, so let us do one very simple exercise. Let a comma b belongs to G. Okay, where G is a group. Then AB whole inverse. Okay, this is same as B inverse A inverse. Okay, AB whole inverse is same as B inverse A inverse. Okay, so how do you do it? So let A comma B belongs to G, and let, so we have to take one identity element. Let E belongs to G be the identity. Okay, be the identity. Right, so I have to show that the inverse of this AB or A star B is B inverse A inverse. Okay, so how do I show that? We already know that inverse is unique. So if I are able to show that the product of B inverse A inverse with AB is identity, okay, then we are done, right? So we have AB belongs to G, A comma B belongs to G implies A inverse comma B inverse, they are also members in G. Okay, this is by property of group. Every element in a group will have its inverse. Okay, and also so let us take AB multiplied with B inverse A inverse. Okay, so what is that? So it will be something like AB multiplied with B inverse. Okay, the whole thing multiplied with A inverse. Okay, so I have applied associative property. Associative property. Okay, so if you are getting confused, I can just write star here. A star B whole inverse is B inverse star A inverse. Okay, so let me write it with star. Right, so it's A star B multiplied with B inverse star A inverse. Okay, so again I apply associative property. So this can be written as A star B inverse. Okay, and then whole thing star A inverse. Okay, again associative property. And then instead of this instead of B star B inverse, I can write identity star A inverse. Okay, and what is A star E? A star E is again same as A, so it's A star A inverse, so which is equal to identity. Okay, so ultimately I have got that A star B when multiplied with B inverse star A inverse gives you the identity element. Okay, so immediately we can write by uniqueness of inverse, we get AB whole inverse is same as B inverse star A inverse. Okay, so for any group this is always true. Okay, so these are some notations and some examples. So in the next lecture we'll start with subgroups, okay, and the definition of subgroups. So we'll have a live session in between for your doubt clearing, so I'll give you the link. Right, thank you.